Good afternoon, everyone, and welcome to our webinar. Thank you for joining us this afternoon. My name is Jomana Tariq Abdurazak, and I'm studying for a master's degree in petroleum engineering at University of Houston. I will be your moderator this afternoon. Today, we're pleased to welcome Dr. Hatem Farouq Ewida, a very special guest from North Sinai Petroleum Company for exploration. Dr. Hatem Farouq Ewida has worked extensively in oil and gas industry in both technical and managerial positions, with local and international companies such as GOPCO, Petroleum, British Petroleum, and now North Sinai Petroleum Co., where he is currently the Exploration General Manager and board member of its JV. He holds a bachelor's degree, diploma, a master's degree, and a PhD in geology, petroleum geology, and geophysics. Dr. Hatem has taught industry-tailored and university courses, as well as published and reviewed several research papers with local and international journals. In addition, he supervised and refereed many PhD and master's degree programs. He is also a board member of the Egyptian Geophysical Society. And today he will share with us his expert opinion on advanced seismic techniques. If you haven't already, please make sure to check out our previous videos on PioPetro YouTube channel and join our Facebook page, Arab Oil and Gas Academy, for the latest updates on our upcoming courses. Please feel free to send your questions in the chat box and we will answer as many questions as possible. With that, I ask you to give your full attention to Dr. Ewida and help me in welcoming him today. Please welcome Dr. Hatem Farouq Ewida. Hi, Dr. Ewida. Thanks for joining us today. We're so glad to have you on PioPetro.
Thank you very much, Jomana. It is, I'm very pleased to join you actually, and it's my pleasure to be with you all today for my fifth lecture. So, hello everyone. I'm glad to be with you today for my fifth lecture about the advanced seismic techniques. Actually, you can call it also non-traditional seismic applications. In this technique, we'll spend, in this lecture, we'll spend almost around an hour that we'll gonna cover the contents in this lecture. It takes time, sorry for that, but today we'll cover an interesting subject, which is the advanced seismic techniques, or we can call it sometimes the non-traditional seismic applications. Some of these applications are very recent, and others are actually from long time ago, but it has a lot of advances in the current days. So the contents of our lecture today will start with reminding you by the seismic method objectives. This will be followed by finding out how can we improve the subsurface image. Actually, we'll study that, or we'll show that through three main categories: through seismic acquisition, seismic processing, and seismic interpretations. And in the acquisition, we will cover three main technologies or techniques, such as the ocean bottom seismic, the multi-component seismic, and the time-lapse seismic, or what we call the 4D. In the processing, I choose the migration or the imaging, what we call imaging, and I choose also two of the most recent techniques that they are applied a lot in the industry now, which is the RTM and the FWI inversion. Then in the interpretation, we'll cover the seismic attributes. Actually, I will remind you with the seismic attributes and how we can use it to improve the subsurface image. This will be followed by some other major categories, actually, like the DHI, or the direct hydrocarbon indicators, then the AVO or AVE, amplitude versus offset, or amplitude versus angle, and we'll know the difference between them. And then we'll have the seismic inversion, and we'll close our talk or lecture by a hint about the machine learning and artificial intelligence application in the hydrocarbon exploration or in the geosciences. So as you all know, we acquire the seismic data from the surface of the earth, and we receive the reflections also on the surface of the earth. And what we want to get, or what the output that we need from seismic data is imaging the subsurface geology. And to remind you, is we try to image the structural imaging, or second stratigraphical imaging, or reservoir and lithology imaging. So we try our best to extract the true image of the subsurface. So we'll start with the ocean bottom cable, or the ocean bottom acquisition. And the ocean bottom acquisition is a marine seismic acquisition approaches. Actually, it is being used in the last decades. The ocean bottom cables only work in shallow water area, actually for the depths of 1 kilometer, the maximum in case of using cables. But there are new techniques which are the nodes, and in nodes we can cover from shallow water, few meters, to very deep waters, actually for thousands of meters, couple thousands of meters. So this is what you see in front of you. This is the photo for the ocean bottom cable. Let's use the laser. So this back to this picture, what we see here is the ocean bottom cable acquisition. So this is a receiver chip that has the cable laid out on the sea bottom, and we have another vessel that carries a source of energy for the seismic. And we have the receivers laid out on the sea bottom itself. This is can happen in using the cables, but as we mentioned that as a very deep water, we can use nodes. And what are nodes? It's like boxes like this, and each box include or contain receivers from the two types, so the hydrophones and geophones, as I'm going to show you now, what we call the dumbbell geophone and the hydrophone, and we'll understand why I use all of this. So the nodes actually, it is difficult to be laid out on the bottom, the sea bottom. So because of that, it is being distributed across long areas, actually from 400 meter to 1,000 meter apart from each other. But we overcome that by using the sources at finer grid or denser grid, about 50 meter to 50 meter. So, for example, to see the benefits of the ocean bottom cable, ocean bottom node acquisition, or generally the ocean bottom seismic, if you take a look on this vertical seismic section and you try to interpret it, this seismic section is recorded by the normal streamer, the conventional seismic acquisition. So you can see the reflectivity. You may recognize some terminations around, like here and there. But if you compare this with the same section, but it is extracted from the ocean bottom survey or ocean bottom acquisition, you can recognize now that these are faults and they are imaged very well, as you see. So we image the subsurface in a better way now using the ocean bottom cable. So let's see other examples to understand these benefits or enhancements. This is another 2D vertical section, and the areas that I've highlighted here, this is the area that has the reservoir in this area. You can see the reflectivity, but it is not very smoothly continuous or clear. So, but if we acquire the same data using the ocean bottom seismic, so you see how the continuity appears in beautiful continuity actually, and you can recognize where the top and base of your reservoirs. So in addition to this enhancement in the subsurface imaging, there are some other benefits for the ocean bottom seismic, which actually I can use this in the development phases because in the exploration phases, when I explore some new reservoirs and I drill wells, for example, in the marine, I will have this sort of facilities like platforms and so on. These facilities comprise obstacles for acquiring conventional seismic data using the streamers. So we use the ocean bottom survey instead. Also, when I laid out my receivers on the bottom of the sea, I can get the benefits if I'm acquiring land data. Same like if acquiring land data. So I can receive reflections from different directions. This is what we call full azimuth recording, full azimuth acquisition. Also, another benefit of the ocean bottom acquisition is the multi-component or the 4C that we are gonna talk about, which is one of the techniques that we cover in our lecture. So the multi-component seismic or the 4C came as a solution to most limitations of the most limitation encountered by the P-wave acquisition. P-wave acquisition is like if you receive your data by the hydrophone in the marine or the geophone on the land. So this is a P-wave imaging. Because we're recording different components, the multi-component is different component. What are these components? The components are both P and shear waves. So I will record primary waves and shear waves. This is allowed the interpreters or the geophysicists to understand more and understand more the subsurface and describe more the reservoir. So, because the conventional seismic technology measures reflected pressures actually, but in the multi-component we record the shear waves. And I'd like you to concentrate with me in this figure here. So if I have P-wave incident, which is a normal acquisition that I use, when it touches the interface between two successive rock units, you know that some of the incident energy will reflect back to the surface, and the rest will refract to the next layer. There is another criteria happened that is when it is reflected back to the surface, it is mode converted. So if I have P-wave incident, in its reflection at a certain angle, it is mode converted into P-wave and S-wave. In this situation, we call the incident energy as PP, and the reflected energy as the reflected P-wave as PB and the reflected shear wave as BS. And this is the same for the refracted part. So we have what we call the mode conversion. So by what I mean, naturally, I will have shear waves. So why don't I record these shear waves? Okay, so from where the source of these shear waves is the mode conversion of the P wave. So if I'm in a marine acquisition, so you know that the shear waves do not propagate in the fluid. So I have to use the ocean bottom cable, and which is one of the benefits of the ocean bottom seismic acquisition. So either cable or nodes actually. And when I put this on the sea floor, so I can, on sea floor is land. So I can use the gumbaled geophone and the hydrophone. So I will have a hydrophone in the water, okay, and I will have 3 geophones. Why I have 3 geophones? One of them will measure the P wave, the reflected P wave, and one of them and the other 2 will record the reflected BS wave. So do I have 2 shear waves, 2 types of shear waves? Yes, I have. It depends on the direction of the particles propagation. So I have what's called the vertical shear wave and the horizontal shear wave, as it is represented here by the X and Z, or the Y and Z. Okay, so I will, in this situation, I have 2 sensors one geophone and one hydrophone that record the P reflected waves, and I have two geophones that recorded the two shear components. Okay, because of that, I have multi-components, and this is why I call it 4C. So C stands for component, and 4 because I use 3 geophones and 1 hydrophone. So now I will have both recording. I will have the P and S wave. This gives me actually great chances, great advances to understand the lithology and the fluid actually in the rock themselves. So let's see examples to see how these 4C enhance our data. So taking a look on this vertical section, you see this black arrow. I have a reservoir section in this area. Okay, you can see that you can say that this is the reservoir section. Actually, if you take a look, this is the P section, the normal conventional P reflection. But if you see the PS, which is the mode converted shear waves, you can see the reservoirs here in very details. Okay, seeing more example in the 3D, for example, the 3D cube, and this is the PP volume, and you know now why I call it by 2 letters, not only P. So it is PP because it is incident as P and reflected as P. And the PS section, which was incident as P and reflected as S by the mode conversion, you see how much is the improvement or enhancement in the reservoir section. You can see the reflectivity, and even you can see bright amplitude around the reservoir, and we will discuss later what this bright amplitude reflects. So going to see another benefit from the multi-component, as I just mentioned, I have 2 components of the shear, and the shear waves propagates in the solids only, not in the fluids. So using or measuring the 2 components of the shear waves, I can know the direction of the fractures within the rock. So I can recognize or study or estimate the fractures within my reservoir. So I can choose which direction, or I can understand which directions that will have more permeability than the other. So I can produce from this side or inject actually to enhance the reservoir production. So this is another benefit from the multi-component or from recording the 2 shear component of the reflected seismic waves. So going to the third method of acquisition that enhance subsurface imaging, which is 4D or the time lapse. And 4D survey is actually a 3-dimensional seismic data, which is acquired at different time spans. So it means that I could acquire data in the year 2000, and after 10 years in the year 2010, I acquire the data with the same acquisition parameter and processing parameter. And this is used to assess the changes in the hydrocarbon reservoir. Actually, what changes will happen in the hydrocarbon reservoirs after production. This time span was used for the production of the reservoir. So I can observe the fluid movement, I can observe the fluid saturation, or the pressure and temperature of the reservoirs. And as you know, the efficient reservoir surveillance is due to monitoring of the reservoir, productivity, or how the reservoir is changed with the production time span. So 3 major areas where 4D seismic is applied to image the subsurface. The first one is monitoring the changes in the producing hydrocarbon reservoir, as we just mentioned. The other one is monitoring the underground storage of the carbon dioxide, and this is a trend in the world now to store the carbon dioxide instead of leave it in the air. And the third one is monitoring the geohazards and landslides and volcanoes and whatever. So let's see what's close to our industry, which is the hydrocarbon industry. So if I have this cartoon that represents the model of the reservoir in 1985, for example. So I will have an oil accumulating at the top of the structure or the top of the reservoir, and I'll have the water at the base. And I will have the water-oil contact, so I can recognize the oil-water contact. After producing from this reservoir, what are you expecting? Yes, you will have this column of the oil will be reduced and the water will getting up. So the oil-water contact will get shallower. So this is after almost 9 years or so from the production. Does seismic reflect that? Yes, this is why I'm using seismic actually. This is why I'm using seismic for the 4D. And D here mean the time span. So I have 3D seismic, and in addition to the time span for the production. So this is the part of the seismic section in 1985, where we can recognize the presence of the oil, which is this yellow color, and this yellow line here is oil-water contact. So after several years in 1996, this is how the seismic will appear. So you'll see that the oil column shrinks, okay, and this line, the oil-water contact should be in this place. So this is how we use the 4D for the reservoir. We'll see another example. So from its application for the reservoir monitoring, we can also find our places, as I will show you, that what I mean, we passed by production. So for carbon dioxide storage, let's see a survey of the subsurface. This area was surveyed in 1994, and within these reflections, there is porous and permeable rock that can store gases within it. Okay, so it doesn't have gases there. So injecting the carbon dioxide inside these reservoirs or storing them and acquiring seismic after several years, you can see that this reservoir or the reflection became brighter. We will understand why it became brighter lately in this lecture, actually. And you can see that you can recognize how much you store carbon dioxide actually within this reservoir. And after some other years, you keep injecting the carbon or storing the carbon, and you monitoring the reservoir and see how is the carbon dioxide stored there or not. So this is how monitoring the carbon dioxide. Okay, imagine if you have, if this is a hydrocarbon, if this is a gas, hydrocarbon gas, and you producing, what you will see in the seismic section. So you will change the name. So you will start in 1994 here, and you start to see the volume of the gases reduces until you finish extracting most of the gas from the reservoir. So let's see another example with the hydrocarbon. So this is part of seismic data, and the color here is for the oil probability. The red is the high 100% oil probability. Okay, and we have 2 wells start to produce since 1992, for example. So after several years of production, and in 2003, we acquired, or the company acquired, another seismic data over the same area with the same acquisition parameter, and to process the data with the same processing parameter, and this is what they've got. So you see that oil probability here get very low because you produced most of the hydrocarbon. So this well produced most of the hydrocarbon that penetrates, while the other well doesn't actually. And you have some bypass hydrocarbon here. So you need to drill another well in this area. So these are the benefits of the time-lapse seismic or the 4D seismic acquisition. So going after that to the how we enhance the subsurface imaging using seismic data processing. And in the seismic data processing, there is a very big step which is called the migration, if you remember my lecture on the processing. And the migration step, we call it imaging, because we image the subsurface actually in a better shape. So the seismic imaging actually has evolved to the point where, with sufficient knowledge of the propagation of sound velocity, of the seismic velocities, we can obtain accurate images before step in 3 dimensions of almost arbitrary complicated geologic structures and lateral change in sound velocities, really with a very reasonable cost nowadays. Actually, the improvement in subsurface imaging using the seismic data processing, it starts from designing the CDB, acquisition of CDB stack, the depth move out. You remember these names from the lecture of the processing, and the digital migration, followed by depth migration and the pre-stack migration, either time or depth. I choose for you 2 actual applications from the subsurface imaging using seismic data processing. One of them is the RTM, the reverse time migration, and the other one is the full waveform inversion, and we'll understand both of them. So to understand how the RTM or the reverse time migration works, we need to know how the other migration or imaging technique works. So the other techniques, which is a conventional wave equation migration, is performed by propagating data downward through a velocity model. Okay, but this will be limited if you have a very complex structure and extremely lateral change in the velocities. The RTM technique propagates this sound wave actually in both downward and upward. So to locate the reflectors or to get the reflection points in much more exact location. It also handling all the types of wave propagation, like the turning waves and the prism waves. The conventional don't handle that. So it is very well in the complex structure and whatever. So let's see a comparison from the real data. This is one of this is an migrated section, which is give me an image, but using one of the conventional actually ray tracing algorithms like the Kirchhoff migration. What you see here is a seismic section superimposed or with the velocity field superimposed in the seismic section. And these colors are for the velocity. This pattern or this shape is a salt dome. This is like salt diapers within the sedimentary sections that we have here. You can see reflectivity here, very well reflections, very nice reflections, very nice reflections. Can you see reflections below or beneath this salt body? I think it is very hard. So let's see the RTM for the same area. So the RTM, you can recognize very well the shape of your salt body. Okay, you can see the edges very well. And you see beneath the salt wall, you see the reflectivity here in the RTM. Okay, it doesn't found here. It is hard to follow. There are some difference actually in the frequency. Here is higher frequencies than this one. So you can get the benefit from each one. So what I mean, you try to enhance the methods of the seismic data to image the subsurface as much real as possible. So if you take a look on this seismic section, which is published by a company called CGG, and this reflects how much details you can see in the reflectivity of the seismic section, vertical section, that generated by the RTM processing or the RTM imaging or RTM migration. So you can follow the reflections from near the surface all the way downwards. You can see how continuous, beautiful continuity, actually, beautiful frequency preserved here. You can follow up the reflector actually across the whole seismic section from your right-hand side to your left-hand side. You can see these tiny faults in this area. You can see how complex is this salt intrusion and affecting the overlies layers. You can see this unconformity surface. You can see this basin, and you see this could be a basement complex highs actually. So you can recognize. So you like see a very beautiful and detailed image for the subsurface geology. So imagine if you invert that. We're talking about seismic inversion now. So going to the second processing technique to enhance the subsurface imaging, which is full waveform inversion, or the FWI. And the FWI utilizes the entire seismic wave field. We use everything in the seismic wave field. From where we have this seismic wave field, this is what the source of energy emits. Okay, so it emits this field, and this field is propagated elsewhere, mainly on the subsurface. So we use the entire seismic wave field to generate very detailed or high resolution refined velocity models. Okay, the velocity is the soul of seismic method. The velocity is the soul of seismic method. So we use this actually to generate very detailed, high resolution, refined seismic velocity model. At high level, or simply, what FWI tries to do is actually quite simple. It iteratively update the initial velocity model, okay, to what I mean, end up with a very detailed seismic velocity model that reflects the seismic reflections that we have. So let's see examples to understand. So if this is the initial velocity model, use this color, each color represents velocity value. You see how smooth is this velocity model, because this is the initial velocity model. This is the first initial velocity model. Then I use this one and migrate my data and then update my velocity volume, do this in several iterations until I reach the final velocity model. You see how much details this velocity model now contain. You see, these are not reflectivity, these are velocity trends, and each color represents a velocity value. So it reflects actually the same subsurface geology, and in each geological formation or whatever, how fast the sound waves that ascend from the surface propagate within it and reflect it back. So again, these colors are for velocity values. You see how detailed are my velocity model. So this is not only, this is also can be refined more actually. So if you take a look on this velocity model, you see how it is detailed, but we call this like a low frequency model. So it could be refined more, or could be of higher resolution, and we call it the high frequency model. You can see how the details in this section or this velocity model comparing to this one. So moving on to the enhancing the subsurface using the seismic attributes, and you know that the seismic attributes is actually like it's a quantity of extracted or driven values from seismic data that we can analyze this in order to enhance the information that might be more subtle in the normal or the traditional reflectivity. For example, this is like a cube of seismic data. This is a reflectivity cube. As you see, you can see seismic reflectivity in different vertical directions in addition to horizontal slicing. So this is normal reflectivity. So I can extract sort of attributes from this seismic volume. The attributes, it depends on the travel time of the data, the amplitude, the phase of the data. I can generate what's called coherency cube. I can generate structural attributes and stratigraphic attributes as I'm gonna show you. So this is a 3D volume of seismic data. You can extract, for example, an attribute that called reflection strength attribute. Each color of this represents the strength of the reflectivity. You know what's the strength? It is the reflection coefficient. So you can see the difference, you can understand the difference between the successive rock unit. You can also generate like a root mean square amplitude volume. It has the same number of lines, same number of samples and everything as the original seismic data. And also you can have the sweetness or the instantaneous amplitude divided by the square root of instantaneous frequency. So you can extract or derive any means of values that reflect something related to geology from the seismic data. Let's see examples. Two major categories for the attributes, which are those attributes that enhance the structural interpretation, and the other attributes that enhance the stratigraphic interpretation. This is again a chair diagram, as we mentioned in the interpretation lecture. This is vertical seismic section, and you can see some terminations here which represent fault. So if I'd like to see the extension of these faults across my whole area that's covered by seismic, I can have extract the attribute across horizontal slices. And what we see here, this is called the most positive curvature attribute. So these red lines represent the faults themselves. The blue colors represent the downthrows of these faults. Also, you can see the coherency slices from the coherency cube, and the coherency is very attractive and very supportive attribute in interpreting the faults. So all this black lineament represents faults actually. And you see here we used a color scheme for plotting, but this is just we use the black and white, so we can see the faults, how the faults are here. So this is enhance the subsurface structural imaging. Also, there are a sort of attributes, other sort of attributes that represent the stratigraphy. So starting from horizontal slices, as you see, whatever in color, whatever in black and white scale, this is a seismic time slice. It's a horizontal slice from 3D cube. And then you can extract like channels. As you see here, you see this, these are channels, okay, which is hidden in the reflectivity. You can't recognize the channels in the reflectivity. Can you recognize this long channel here in the reflectivity? No. You have it now because you extracted some or derived some attributes from the data. Also, you can see the thickness of the channels themselves using stratigraphic attributes like the spectral decomposition. So different names, hundreds of attributes, either mainly some of them enhance the structural imaging or structural interpretation, and others enhance the stratigraphic imaging. So going after that to the direct hydrocarbon indicators, and the direct hydrocarbon indicators actually are anomalous seismic amplitudes. They are anomalous seismic attributes or pattern, okay, and they are of different types. Actually, let's understand why it is anomalous. So this direct hydrocarbon indicator, this mean what's mean by direct hydrocarbon indicator? This means that if I see this anomaly, so it is most probably indicates the presence of hydrocarbon, which means that this reflection is among a hydrocarbon reservoir. This is what meant by that. Okay, so it's an anomalous amplitude. Let's see that. So if you take a look, for example, on this vertical seismic section, you see how the amplitude here is dimmer or faint, and you see the amplitude here is darker or is brighter. Can you find the most brighter reflectivity here or reflector? Yes. These are the most bright amplitude in this area, in this vertical section, and this is what we call the bright spot. And the bright spot represents the top of the reservoir. So if I have bright spot, this means that most probably this is the top of the reservoir. Okay, so it has, why it is anomalous? What's mean by anomalous? It means that it is a localized amplitude of greater magnitude than or comparing to the background amplitude values. So seeing another thing, so I will leave you take a look on this vertical seismic section and find out, do you have any anomalous amplitude here? Okay. Do you see this reflector? Yes, it is bright, but it is what we call the flat spot. You remember the oil-water contact we were talking about a few minutes ago? So this is reflect the fluid contact. So it is either oil-water contact or gas-water contact. It is a reflector, or it is nearly horizontal because I have velocities that affected it. And you will find that this reflector cross-cut the other stratigraphy of the reflectors. So it could cut the reflectors because it is a fluid contact. It's supposed to be like a straight line. It's because of the velocity of the seismic that you can see it near a flat. Do you recognize another anomalous amplitude? How about this? So this is a bright spot here. And I just mentioned that the bright spot is, yes, the top reservoir, and the flat spot is the fluid contact. So if you find this gathering bright spot with flat spots, you are very lucky because you know your top reservoir and where is the fluid contact, so you can calculate the volume of your reservoir very well. So going further to see other types of DHIs or direct hydrocarbon indicators, if you take a look on this vertical section, again, try to find some anomalous amplitude or anomalous criteria. How about these two locations? You will find that you have a blue reflector that turned red, and the red reflector here turned blue. This is what we call polarity reversal, because each color of this reflect the reflection coefficient. One of them is positive and the other is negative. It's supposed to be continuous, okay? But this is polarity. With this polarity reversal, actually can occur where the capping rock, the seal, has a slightly lower seismic velocity than the reservoir. And it could, what I mean, occur when you have the fluid changes from not vertically, horizontally to water. Can you recognize another anomalous amplitude that one we've talking about before? Yes, you have here the flat spot. So here also know where is your reservoir. The last DHI called the dim spot. And if you take a look on these two arrows, the black arrows, you will find this reflector is black and then dim all the way. You have it black here and dim all the way, okay, as you see here. So the dim spot is low amplitude anomalies, and it is caused by highly consolidated sands within a much greater acoustic, with a much greater acoustic impedance. In the enclosed shale, what I mean is softer than the sand. So the acoustic impedance of the shale is lower than the sand. Okay. So, and we recognize that in the very deep seated sand deposits or of old age sands actually. Then we'll go to the AVO or AVA, which is the amplitude versus offset. If I say AVO or amplitude variation with offset or amplitude versus angle, the angle is the angle of incident. Okay, so angle of incident related to the offset, and you know the offset. I will show you now. So it is a variation of the amplitude with offset, and it is actually very important to because we use the AVO on several applications, as I will show you. So we can, if I see directly the carbon indicators, what convince me or confirms that these represent fluids is the AVO. So the AVO will confirm that the DHI is exactly represent fluid. So let's understand how this happens. If you see this normal acquisition, this is a conventional acquisition, not an OBC, for example, but it could work with OBC, of course. So this is the seismic vessel. You have the source here, and you have your receivers, the hydrophones, until the end. So you have, this is a source, this is the first receiver, and you have the last receiver here. So the distances are like between the source and the nearest receiver. The first receiver is we call near offset, and the distance between the source and the farthest receiver we call the far offset, and in between is the middle. So if I record the seismic on an area that doesn't have reservoir, so there is no fluid in the rocks in the rocks at all, so the reflection will near offset have the same amplitude like this is how the AVO works. And as I mentioned, that if I don't have any fluid in the subsurface rocks, so I acquire seismic data in the area with no reservoir, so the reflectivity will come with the same amplitude at the near trace offsets as like the far. So it is the same amount of amplitude or the same value of the amplitude. But if this reflection comes from the interface between a seal rock or a cap rock and reservoir rock, I will have differences in the amplitude values. So this is what you see, and we see that the amplitude is small at near offsets and higher value at the far offset. We call this like increase of amplitude with offset. How this reflects on the seismic data. So if I see seismic data, you see how bright this amplitude. So it is higher amplitude than this area. I will locate it to you. Okay. So to analyze the AVO, to find out that I have AVO anomaly, which means that the amplitude change was offset, I can extract what we call partial stacks, like the near stacks and far stacks, and compare the amplitude actually in the same area. So in this situation, you have the great or the high amplitude at the far offset more than the low offset. So now, if I see this like the hydrocarbon indicator and I apply this AVO analysis, this will be confirmed that there is a fluid, there is a gas or oil within this area. Okay, so this is visually. I can use this visually when I process my AVO data, but I can go more further with AVO. We will talk actually in more details in the coming lecture about the AVO. When we are going to talk about the reservoir characterization. So more is, so you can see the anomaly of the AVO on the pre-stack, which is the CDBs, and you can reflect that on the seismic section itself. In the examples that I showed you, we have increase in the amplitude with offset. This is what we call the class. It's one of the classes. I can have this anomaly like decrease in amplitude with offset. This is another class. So because of that, we have different classes for the AVO have class 1, increasing amplitude offset, and class 2 and class 3. And we have a lot of application on the AVO, like we cross-plotting the data we get from the AVO, so we can recognize where do I have gas, where do I have oil, where are the sand, where is the shale, and this is, as I just mentioned, we'll talk about this in details. I'll give you very good detailed examples about this. So I can also invert the seismic data using the AVO to provide the lithology, the porosity, the fluid content, and the thickness of the basin. You see how strong is the seismic data. You see how much it's like a treasure. So how much we use to enhance subsurface imaging. So this is from the AVO, so I can find on the reflectivity where is I can generate like a fluid factor section and know where is my gas and where is my oil. And I can see the distribution across my area on map view. So going after that to the seismic inversion, and the seismic inversion is essentially a very simple procedure actually. In seismic inversion, the original reflectivity data that you have the seismic section and see the reflectivity on it as typically recorded is converted from an interface property to a rock property. So it will change to density and velocity and B shale and all the petrophysical parameters and rock physics that you know. This inversion is first to go to the impedance, and the impedance, as you know, it is acoustic impedance. It is density by velocity, and from this point you can go to the other petrophysical parameters. So simply, the seismic inversion remove the imprints of the wavelet of the seismic of the source. You know, you send this in the wave. What I mean, the sound propagates in sort of wave. So we try to remove the wave using deconvolution and convert the result into impedance. And it's in this process we get quantitative rock properties, and seismic inversion could be applied in the pre-stack domain, the post-stack domain. We can use different algorithms like deterministic way. We can use it in the random way. You can use the geostatistics techniques to invert our seismic data and get actually the output. If I have geological information like the well data and core data, this will enhance the interpretation or the inversion itself. So simply, if I have this seismic trace, as you see here, I will apply the convolution to remove the wavelet, extract the wavelet. So it will return back to the reflectivities. And from reflectivities, if I have like a low frequency model, we'll understand that more when we talk about the inversion in the coming lectures. And it will end up with a log, which is acoustic impedance log. And in this case, it is an absolute. If I didn't know the low frequency, I will go to a relative impedance, but it's again a log, acoustic impedance log, which is density by velocity. If you remember that trace at the very beginning lectures, you will find it other way. It's a different way. Okay, so going from your right-hand side to your left-hand side, this is the forward modeling, which models the seismic trace. Going from your left-hand side to the right-hand side, this is a reverse or inversion of the seismic data. To see this on real seismic data, this is a piece of seismic section, and you see how the reflectivity goes. This is a seismic trace. You have peaks and the troughs and so on. But when you invert your data, you will get up with like sort of logs, and you have this boundary looks like this. Okay, so seeing another example, if I have this reflectivity, is a vertical seismic reflectivity. when you have peaks and troughs, and if I have some geological information, I can invert this conventional seismic reflection data totally into a sand distribution vertical section. The blue color and blue and purple colors, these are the sand in this area. So it is sand. It comes from reflectivity, as you just see. Seeing more or other more examples, which is using the inversion on the AVO. So if I have this is a near angle stack, so near angle is more or less is a near offset stack. So it is reflectivity, as you just see. You may have some anomalous amplitude here, but if you invert that into P impedance, P means P width. Impedance means again velocity by density. So you can characterize more the anomalies that you see here, that it is become more concentrated. You can locate them very well. And if you invert this more to the Poisson ratio or the VBVS inversion, you remember the multi-component and the ocean bottom cable, and we see the importance of the shear waves. So this is another importance and another benefit. When I use a VBVS, V is a velocity, the VBVS ratio, I can discriminate the fluids and the viscology, as you just see. So from reflectivity, you can identify your reservoir. Okay. Going for our last application, which is machine learning and artificial intelligence. And while machine learning is based on the idea that machines should be able to learn and adapt through experience, artificial intelligence refers to a broader idea where machines can execute tasks smartly. Artificial intelligence applies machine learning and deep learning and other techniques. We will have a separate lecture. The last lecture will be about the machine learning and artificial intelligence, and we'll understand more and more about this. The point here is that you have your machine works like the human brain. Okay, so you know that in exploration you have a tremendous amount of data, and instead of you handling your brain, you can train your machines or your computer, and they can handle all of this data and solve a lot of problems in our hydrocarbon exploration. So, for example, if you will go very deep, actually, not only to know the fluid and the source, you will know the features of the subsurface. So, going from a vertical seismic section like this, full of reflections, just reflections, okay, and you can train, you'll use a machine learning and artificial intelligence, and output like the phases distribution across this seismic line. So you have about 4 phases here. You can identify each phase with color. What are phases? Phases means that this is sandy deposits, or this is muddy deposits, or carbonaceous deposits, or whatever. This is what meant by phases. So you will know where are your source rocks, where are your reservoir rocks, and where are your cap rocks. Okay, seeing more example for this, if I have this reflectivity from a far angle stack, far angle mean far offset or more or less, so you can, and you have like porosity from some drilled wells, few number of drilled wells, and you can distribute your porosity using these wells, then you will train your machine to find a relation between the porosity and the seismic reflectivity, and then ask your machine to generate the porosity distribution from your seismic data. You will end up with this. This is output of the machine learning. You see how detailed is the porosity distribution. Actually, it's much detailed and more accurate than what I get from the sparse wells. Okay, and also you can define where are your direct hydrocarbon. You expect to see direct hydrocarbon indicators in your seismic volume. Furthermore, the phases change from reflectivity you can go to the fishes distribution in your area. With this slide, I conclude my presentation. I wish that you get the benefits you were expecting. These are, again, my contacts. And please, if you have questions, I will be very happy to answer.
Thank you, Dr. Hatem Farouq Ewida, for this enlightening session. Normally, we'd move to answering questions in this duration of the webinar, although it seems like our honorable attendees don't have questions today, so that's about it. It was a pleasure having you on PyPetro, Dr. Hatem Farouq Ewida. Thank you very much for joining us, and thank you everyone for tuning in with us today. Today's session will be uploaded on PyPetro YouTube channel. You might want to check that out for your quiz. Thanks again. Have a great day.
Thank you.